Hi, I'm Dane Quinn from the University of Akron, and welcome to my series of video lectures for engineering mechanics. Today, I'd like to give you a video lecture on equivalent springs, in particular as motivated by a problem that has pulleys. So let's get to it. So here we see the system. I have two pulleys that support a block of mass M. Now, these pulleys are massless, and a radius r is 10 centimeters, as given here in the statement. And then we have three springs that support this system. Notice that the spring on the left here is then connected to a cable which wraps around the left pulley, which then wraps around the right pulley, which finally is connected to another spring attached to the ground. And the pulley on the left is also connected to the ground with a spring. Again, each of these springs are identical, of stiffness K. So what I'd like to do is model this system and find the natural frequency. Then, if I pull the block down from its static equilibrium position by delta equals 8 centimeters, so basically I'm taking this block and I'm moving it down by 8 centimeters and then releasing from rest, I want to find the resulting motion. So in particular, this pulley and in this pulley system acts like a single spring. So what we'll find is that we can replace this entire pulley system with a single spring that has a specific spring constant. The fact that these pulleys are massless is actually important. If, in fact, these pulleys did have mass, the degree of freedom of the system would be much larger. You can actually work it out. It'd be a 3 degree of freedom system in that case. However, because these pulleys are massless, it reduces the degree of freedom for the overall system to 1. We really only need this single coordinate to describe the location of the block. So, again, this is a single degree of freedom system. So we should be able to identify equivalent mass. In this case, there's no damping, so the equivalent damping would be 0. But finally, an equivalent stiffness for this system. So we always begin by thinking about what's going on. Here, this block moves up and down. As this block moves up and down, this disc is free to rotate. The cable connecting these two is inextensible. So the position and rotation of this disc will then specify something about the position and configuration of this disc. But it too is allowed to move up and down and rotate. So here, I'm going to consider three objects. And I'm going to consider the two pulleys separately from the block. So looking at the forces that act on this system, right? We have a force from this spring on the left. Right, so that'll be there. We have a force from the spring on the center of this pulley. And then we have a third spring over on the right. So we have spring forces. And these forces arise from the three springs. We'll call those F1. F2 and F3. And then we have a number of other forces that act on this system. In particular, we have a reaction force from this cable that connects the two. So the reaction force we will define as R. Now, it's an internal force because we cut this cable to identify the forces. So these two must balance out. And this becomes minus R. Finally, I've got forces that arise from the cable connecting the center of the pulley to the block. And we'll call that the tension. So here, that tension is going to act on the block, and then also on the center of this pulley. we'll label that as T and minus T. Once again, these are internal forces, so they have to balance out. Now, since we're measuring the block from static equilibrium position, right, in particular, we're pulling it down from static equilibrium position by a given distance, makes sense to measure from that point. So we're going to neglect the influence of gravity here. Gravity essentially would take care of where that static equilibrium position is. And then when we measure from that, again, remember that we don't include it in the modeling. So we neglect gravity as a consequence of measuring from static equilibrium. Which brings us then to actually the coordinates and directions. So here we have our system again. Start off with directions. Makes sense to define I and J. Here I is horizontal, J is in the vertical direction. And then we need to identify the coordinates that we need for both the motion and the forces. So for the motion, let's identify the block as B, and then we'll measure the displacement of this block with X. Measure down, again, if X is equal to 0, we'll assume this is in static equilibrium, right? So X measures the displacement down of the block. So once again, we need coordinates and directions, and the coordinates will be used for the motion of the block and the forces in the springs. Each spring can undergo a different displacement. So I'm going to measure a coordinate that describes the displacement or the stretch in each spring. So we'll start off with this one. Let's call this point A. So as measured from the, again, static displacement of this spring, we'll define Z. Let's go and use a point C here. So the stretch in this upper spring we will identify as Y. And then finally, let's go and define two other points. This point we'll need in a second. Let's call this D. And E will measure the stretch in the spring on the right with a coordinate W. So once again, each coordinate vanishes in the static equilibrium position. Which is what allows us to neglect gravity. Now we turn to the kinematics. The acceleration of this block is what we'll need for the motion. It's actually relatively straightforward because we defined x to be the displacement. So again, the acceleration of b is now minus x double dot in the j direction. If x is positive, we're displaced down. So then if x double dot is positive, we're accelerating in the minus j direction. But we do have a number of other equations that we need to think about. And in particular, how are these various coordinates related to one another? Because this cable connecting the two pulleys is inextensible, right? So that provides a constraint. One way of thinking about this is that the length of the cable from A wrapped around this pulley through D wrapped around this pulley and to E is constant, right? So that's going to give us a relationship between all four of these coordinates. How do we do that? Well, I always find that the easiest way to relate coordinates is by relating velocities. So for a given pulley, we know that the velocity on the left, so think about this pulley, the velocity over here on the left, which is essentially the velocity of point A, is equal to the velocity of the center plus the angular velocity of the pulley cross the position from the center to the left side, right? Or left with respect to the center. We can do the same thing for the right side of the pulley. So the velocity on the right is the velocity of the center plus the angular velocity of the pulley across the position of the right with respect to the center. Now, the thing here is that this vector from the center to the left, right, so that would be over here, is the opposite of the vector from the center to the right. So in fact, these two terms are opposed to one another, right? So whatever this is the negative of that. In fact, adding these two equations together, we see that the velocity on the left plus the velocity on the right of the pulley. Again, I'm just adding together the two left-hand sides, and then I'll add together the two right-hand sides, and these terms cancel. So that's going to be twice the velocity of the center of the pulley. And we can use this relationship on each one of these pulleys. So let's look at the pulley on the left first. On the left side of this pulley is the velocity of A. VA. The right side of the pulley is the velocity of D. VD. And that's going to be twice the velocity of the center. Right, so that's going to be 2 times VC. In addition, on the pulley on the right, the velocity on the left is VD. Again, each point on this cable has the same velocity because it's an extensible. So this point on the left, well, this point on the right side of this pulley has to have the same velocity as this point on the left side of this pulley, and those are VD. So then plus the velocity on the right side of that pulley, which is VE, is twice the center, VB. Okay, well, every single one of these, with the exception of VD, I have a coordinate for. So let's eliminate this quantity. Well, that means that the velocity of A plus 2 times VB minus VE, right, that was the velocity here, equals 2 times the velocity of C. Or the velocity of A minus the velocity of E is equal to twice the velocity of C minus the velocity of B. Now we can go and use the coordinates that we have. Well, the velocity of A was Z dot in the J direction. The velocity of E, that's minus W dot in the J direction. The velocity of C was minus Y dot in the J direction. And then the velocity of B is minus X dot in the J direction. So finally, looking at this relationship, we're able to, again, find a constraint between Z and W and Y and X. Given this equation on the velocities, I essentially integrate with respect to time, and I turn this into a constraint on the coordinates. And that looks like Z of t, right, again, integrate this term, and then plus W of t is equal to, I'm going to factor out a negative sign from here, minus 2 times y of t minus x of t. So this pulley system introduces this constraint between the coordinates. And that just comes from the kinematics. Next in line, we have our free body diagram. So once again, I've shown the problem with all the coordinates defined. And this was our force diagram. So each spring is written in terms of the corresponding coordinate. So we defined coordinates that really helped us describe each of those spring forces. And then the internal forces are just unknown. So let's go and try to fill in the blanks. For this force from this spring, we have minus k times z in the j direction. The force acting on the center here, well, if y is positive, that force pulls up, so we get k times y in the j direction. Again, these two forces are internal, and we refer to them as the reaction force. So this we'll say is r, j, and this is minus r, j. Our third spring force is k times w in the j direction. And then we have this tension between the pulley and the block. So if this force is Tj, this is minus Tj. Again, all of the springs are related by constitutive laws, right? K times displacement, or stretch in the spring. And the internal forces are in terms of unknown magnitudes. So we have the kinematics, we have the forces, and all that's really left to do is apply the equations of motion. So we want to apply linear and angular momentum balance to each object. And it doesn't matter if it's a pulley or if it's the block. The equations of motion and the laws of mechanics, momentum balance, has to be satisfied for every object, for every part of every object. Right? So even though this pulley is massless, it still has to satisfy momentum balance. We're going to call this pulley C. C here is this point at the center. We'll actually refer to this as pulley B. Again, B can be identified with the center of this pulley. So let's look at pulley C first. And to start off with, we'll look at linear momentum balance. Sum of the forces equals mass times acceleration. But since the pulley is massless, sum of the forces has to be equal to 0. Again, the mass is 0. Not to say that the acceleration of this pulley is 0, but because of the mass being 0, the forces have to balance. Well, add the forces together. Let's do that in orange. So k times y minus k times z minus r in the j direction equals 0. Also on pulley C, sum of the moments about the center of the pulley has to be equal to 0. Again, it's massless, so there's no rotational inertia. Well, from here, this spring acts at the center, so the moments arise from the two forces on the edge. Well, again, moments are r cross f. Just to remind you. So the moment on the right is k times z times the radius. And then the moment on the left ends up working out to be minus r, the reaction magnitude, times the radius. And that's in the k direction. We'll do the same for pulley B. Sum of the forces equals 0 because it's massless. And I have r minus t plus k times w, this is in the j direction, equals 0. Again, the moments have to vanish. Here, the moment is K times W times R, that's the moment from this force, minus capital R times R, radius, in the K direction equals 0. Finally, we have the block. Now, angular momentum balance for the block is trivial, right? The block doesn't rotate and no moments are produced. So I'm not even going to write this down. If I did, it would be 0 equals 0. Linear momentum balance, though, is sum of the forces equals mass times acceleration of the mass center. So this provides to us T in the J direction. That's the only force that acts on this block. I'll remind you we're measuring from static equilibrium. So we've neglected gravity. And that equals M times minus x double dot in the J direction. Because, of course, x is defined positive down. So these are our equations. Again, I'll remind you that the massless pulleys still satisfy momentum balance, both linear and angular. So with this, we're ready to go and reduce this to our sort of common single degree of freedom form. I've rewritten the 5 equations that we had from momentum balance, right? 1, 2, 3, 4, 5. And the constraint equation that we identified previously. Notice that these are from pulley C. These are from pulley B. This is momentum balance applied to the block and our constraint equations. So we see 6 equations. 1, 2, 3, 4, 5, 6. And we have 6 unknowns. We have x double dot as well. That's considered one unknown. We have y. Y is this coordinate. We have z. We have w. And then we have these 2 internal forces, r and t. So 6 equations, 6 unknowns. We can solve this. You know, in general, if I had 6 equations and 6 unknowns, that would be a lot of algebra. In this problem, and really in most of the problems that we do, the algebra is not quite as bad as it might first appear. These unknowns appear only in a limited number of equations. So if I look at x, for example, x only appears in 2 equations. W only appears in 1, 2, 3 equations, right? R appears a number of different places. But the idea is that just pick a simple unknown to eliminate that. And then pick another unknown that's relatively simple to eliminate. Okay, eliminate that. So here's one procedure that works. The first thing I'll eliminate is t. Notice that right here, I find that t is equal to minus mx double dot. Then I'll choose another one to eliminate. Let's look at this equation and solve for r. Right, so here r is equal to k times z. So we're just going to kind of do this in process. Why not choose r as kw? Well, because either way it'd be fine, right? I just happen to choose this one. So let's go and eliminate from the remaining 4 equations t and r. Right, so this first equation becomes k times y minus k times z minus k times z equals 0. This equation I already eliminated. And then the second equation here becomes k times z minus mx double dot plus k times w equals 0. This equation is k times w minus k times z equals 0. And then finally, my constraint equation reduces to z plus W equals minus 2 y minus x. So that actually stays unchanged. Okay, do it again, right? Find a relatively simple coordinate to eliminate. Now I'm going to make use of this equation. And notice that z is equal to w. Okay. And then from here, we find that y is equal to 2 times z. Again, this is ky minus 2kz, which, of course, is, because of this, equal to 2w. So let's eliminate z and y from these equations. We've taken care of that one. This equation becomes k times w plus mx double dot plus k times w equals 0. This I used to identify z and w. And then finally, my constraint equation becomes w, that was z, plus w, right, from here, equals minus 2 times y. Well, that's 2 times w minus x. Okay, so looking at this relationship, I have 2 w's on the left, I have minus 4 w's on the right, so I'll bring those over, and 6 times w is equal to 2 times x. So w is x over 3. Finally, using this equation, we have mx double dot, and then we have 2kw, but w is x over 3 equals 0. So at the end of this, right, let's rewrite this, simplify it a little bit. Mx double dot plus 2k over 3 times x equals 0. So there you go. The equation of motion for this system. I asked you for the natural frequency. Notice that k equivalent, the equivalent stiffness, is actually 2k over 3. The equivalent mass, of course, is just m. So the natural frequency, square root of the equivalent stiffness divided by the equivalent mass. So this simplifies to 2k divided by 3m. Great. Now, let's go and do a little more. Ultimately, I'll find the response like I asked you in the problem statement. But before I get there, I want to really talk about this notion of equivalent stiffness. If I look at this pulley system, it's attached to the mass, and it provides some stiffness, right? This is where the 2k over 3 times x term came in. Well, I can think about that stiffness as, again, an equivalent spring. Or, if I look at the point B, if I pull this down with force T, this was the tension, I can ask, well, what force is generated? So the tension in the cable, remember, was written as minus mx double dot. That was from linear momentum balance applied to the block. And from our equation of motion, we found that mx double dot plus 2k over 3 times x is equal to 0. So solving for mx double dot and using it to identify the tension, we see that T is related to the displacement by something that looks very familiar to a spring, right? In fact, it's equivalent to a spring. And this 2k over 3 looks like the equivalent stiffness of the system. So in fact, this system, right, this pulley system with the mass, is identical in terms of the equation of motion to this system shown on the right, where we have, again, a mass, a block of mass m, and we have just a simple linear spring, but now the equivalent spring constant is chosen as 2k over 3 rather than something else, maybe k. But if I write the equations of motion for this system, I would end up finding that mx double dot plus k equivalent times x is equal to 0. And with k equivalent equal to 2k over 3, I have exactly the same equations of motion as I have for this complicated pulley system. So really, what we find is that this pulley system is equivalent to a spring with stiffness 2k over 3. So finally, let's look at the response. The problem statement gave me parameters in terms of mass and stiffness and that sort of thing. So for the given parameters of the problem, the equation of motion given here ends up as 20 kilograms, that was the mass, x double dot, when I calculate 2/3 times the stiffness, remember the stiffness was 480 newtons per meter, I end up with 320 newtons per meter times x is equal to 0. We also need initial conditions. Well, we took the mass and we pulled it down by 8 centimeters, right? So moving this down is an initial displacement, initial value of x that is equal to 8 centimeters because x is positive down. And it was released from rest, so the initial velocity is 0. Now, with these parameter values, we find that the natural frequency, again, 2k divided by 3m, gives me a numerical value of 4.9 radians per second. Right, so we have the natural frequency, we have the initial conditions, we can find the general response. We've already developed the general solution for both a damped and an undamped system, single degree of freedom system. And for an undamped system, it looked like A sine omega nt plus B cosine omega nt. And recall that A and B are arbitrary constants used to fit the initial conditions. In addition, we can take the derivative of this and find that x dot is equal to A, again that arbitrary constant, omega n cosine omega nt minus B omega n sine omega nt. Essentially, I just take the solution, take the derivative. Well, using my initial conditions that we gave in the problem statement, delta was the initial displacement. And evaluating this general solution at t equals 0, well, sine of 0 is 0, cosine of 0 is 1, so we just find B. Likewise, for the initial velocity, that vanished. And evaluating the velocity at t equals 0 gives me A times omega n. So now I have two equations. I have B is equal to delta and A omega n is equal to 0. Well, that's easy to solve for. And that gives us our general solution. X of t is equal to B, which is delta, or 8 centimeters, times cosine omega n, well, that's 4.9 radians per second, times t. And this is the response of the system when I displace the mass initially by 8 centimeters and release from rest. Notice that it oscillates about x is equal to 0, which in this case physically corresponds to the static equilibrium position. And in general, these kinds of systems, they do. They oscillate about static equilibrium. So if I displace it down, it essentially oscillates with a mean value that is equal to the static equilibrium displacement. So that's it. This is an example with a pulley system that gives rise to an equivalent spring in the system. You've seen equivalent springs before in earlier classes. You had parallel combinations and series combinations of springs and dampers, and there you kind of know how to combine those elements. But this is a more general case of an equivalent spring, right? It's not a spring in parallel, two springs in parallel, or two springs in series, right? Instead, it's a relatively involved component. Yet the net effect is identical to a linear spring with a specific spring constant. So that's it for today. Thanks a lot. As always, I'd love to hear your feedback, any questions or comments. You can leave a comment on the video. You can email me. However you need to get in touch with me, please do. Thanks so much, and I will talk to you again. Bye.